Now let us see how this is done in the internet now practically. The first thing is that in the internet, we don't use the DEC bit like in the DECnet architecture. We use TCP to do congestion control. Why do we use TCP? Well, the true reason is it was forgotten. When TCP and IP were invented, there was no congestion control. And then when the congestion collapse occurred, people very quickly thought, well, let's fix it. How can we fix it? Well, to fix it, the idea was let's do this additive increase, multiplicative decrease. So we need to send feedback to the sources. What is the standard mechanism by which a source can receive feedback? Well, if that source is using TCP, then there are acts and lots of things in the TCP flows that makes it a natural place to put this. So it comes as a natural place to put something that we need. Now there are also UDP sources. But when this was done, UDP was not used for video or audio streaming. It was used only for going to the DNS or a few things like this. If you have UDP sources and they create a lot of traffic, and if your UDP application does not implement a form of congestion control, then you are back to what we saw last week. You have an uncontrolled network. Congestion collapse may occur. So UDP sources are a problem for the internet if they create a lot of traffic. So as we will talk perhaps a bit later, UDP sources that are long-lived sessions, either if they live in a network like the internet, if they live in a network like the internet, they should make some mechanism to prevent congestion collapse. And the dogma in the internet today is they should be TCP friendly. In other words, they should exhibit a rate control that, at least roughly speaking, has the same properties as what TCP does. We'll talk more about that a bit later. Otherwise, if you don't do that, you need to control your network differently. There are different ways to control a network. We have seen that you can have networks that have SDN functions where we say we have some UDP flows that are uncontrolled and we allocate some link resources and priorities to those flows. We will talk a bit more to that. That's another way to do it. But that means the network is centrally or globally controlled by every rate here. But I would say the overwhelming case in the internet is that we use TCP. Now, the problem with TCP is in the internet there is no DEC bit. There is not a bit that is sent back to the source, the Y bit that says Y = 1 means congestion. So the designers of the internet TCP at that time, Van Jacobson and Sally Floyd, they thought it's a good idea to use the loss as an indication of congestion. So the Y that a source receives is a loss. If a TCP source sees a packet being lost, it thinks, oh, this is an indication of congestion. This is how TCP congestion control in the internet works today. We will talk about it more, what it means a bit later. Of course, there has been attempts for 20 years to try to introduce the DEC bit. It's called ECN in the internet. We'll talk about it a bit later. How can we control the rate of a source using TCP? Well, the natural thing is to use this window formula here. This window formula says that if I have a window flow control protocol that has a window size W over a path that has a round trip time RTT, then as long as there's no losses, at least, the rate that is reached by this, if there is no other bottleneck, will be W divided by RTT. This is used conversely now to say, if I want to control the rate of a TCP connection, then by controlling W, I will reach the same. At least as long as there's no loss. And we will see it has an impact. When there are losses, this formula breaks and we need to do special things. But that's the idea. So if you want to give to a TCP connection a small rate, you give it a small window. If you want to give it a high rate, you would give it a high window. Now the window is controlled by the advertisement field of the destination. This is called flow control. The goal of this advertisement, the window size, is to protect the resequencing buffer at the destination. How can we additionally control the window? Well, this is done simply by having every TCP source has an additional variable associated with a connection that is called the congestion window. In the literature and in the code, it's called usually CWND. So every TCP connection in every direction has the offered window that comes from the window advertisement, the field in the TCP acknowledgements in the reverse direction. Plus, there is a local variable associated with connection, which is congestion window. And the actual size of the window is the mean of the two. Why the mean? Of course, you cannot go above the offered window because you need this offered window to protect the receiver, resequencing buffer. And you also want to be at the congestion window. That's for protecting the network. That's congestion control. So a TCP machine will need to compute locally its congestion window. In contrast to the offered window that comes from the other end. You don't compute it, you just simply see what is in the header of the packets that come. Here you have to compute it locally. And you compute it locally using essentially additive increase, multiplicative decrease, which means when you receive negative feedback, in other words, when you detect a loss, then you decrease the window by a factor of 2. That's the multiplicative decrease. And when you receive feedback indicating that there is no loss, which for TCP is simply receiving acknowledgements. When you receive acknowledgements, we will see in detail how this is done. When you receive acknowledgements, you interpret this, well, things are going well, the packets that I've sent have not been lost. So you interpret that as a feedback that there is no congestion. And then you increase additively. And the additive increase is by adding one maximum segment size to the window size. Here we find a conflict between the mentality of TCP, which is byte-oriented. It's a stream-oriented, it counts in bytes. But when it comes to the window and here it counts in packets. Well, we have to live with those contradictions. So this is AIMD, additive increase, multiplicative decrease. Plus we have seen that we find it useful to complement AIMD with something to reduce the size of the transients, which is multiplicative increase. And here the factor is 2. That means at every time slot we multiply by 2 when we receive positive feedback, which means when we receive acknowledgements. Then there are additional bells and whistles that we will discuss in detail, which have to do with that the theory is not as simple as this, because when there are losses, the rate is not exactly given by the window. But we'll talk about that in a minute. Here is, for example, a trace that we can do by observing the size of the window, congestion window, at a TCP source. Slow start is implemented also by a window, not by a rate, which is called the slow start threshold, or the target window, which is shown in red here. So we see here those are traces taken from, those are data constructed from a trace and taken from this paper. We see that in slow start the window increases until you see a loss. Then when you have the first loss, you decrease the target window by half the value it has reached. That's exactly what we had seen a minute ago. Then you start again, and here there are three slow start phases. And at this point you end slow start. And after slow start, you have this additive increase, which should be linear, but here is more concave, sublinear. And then again, you have a loss. When you have a loss, this is interpreted as a negative signal. So in TCP, when there is a loss, what we should do is decrease the window by 2 and continue. But for good or bad reasons, the things are done a bit differently depending on how the loss is detected. If a loss is detected by timeout, it's considered in TCP philosophy, let's say, it's considered to be a bad case. Normally, most losses should be detected by fast retransmit. Fast retransmit, correct. duplicate acknowledgements being seen, you see these duplicate acknowledgements, and then you detect the losses. If you detect a loss by timeout, it's probably something has gone wrong, which is illustrated on this trace here. We see that the window does not increase, which means there's probably a long period of time where nothing is coming back. There is no acknowledgement coming back, so the connection hangs for whatever reason. And then there is a timeout, which might be that there is severe congestion somewhere. So the philosophy is, when there is a timeout, there is severe congestion, which is interpreted as a change of condition. The network has changed. A link is broken, or all of a sudden there is a surge of more traffic somewhere. In a case like this, we interpret that as we are, again, like at the beginning of a connection. So we should do slow start again to test the water again, not simply increase from there. So whether this is good or not, this is how TCP does it. So here we will go into slow start. That means when there is this loss detected by timeout, we put a target window, which is half the window that was there just before the losses. And then we don't set the window here, but we restart from scratch, from 0. We send the window has the minimal value, which is 1 or 2 packets. And then we increase exponentially until we reach that value. This is the end of slow start. And then we continue increasing linearly. This is the first complexity. There is this little slow start thing that comes in the middle. For long-lived connections, slow start is typically like this. This is a little blurb. But if we look macroscopically at this trace, we see that it is linear increases interspersed with sudden decrease by a factor of 2. It's like the stock exchange values. It increases until it crashes. So here it's the same. And in average, it provides what we do. Now, how are multiplicative increase, multiplicative decrease and additive increase implemented in reality? In the model we saw before, everything was simple. We had a discrete time model. I had the source xi of t. At every instant t, we do xi of t plus 1, etc. So we had a mental model that was synchronous. In reality, you're doing TCP codes. I mean, how do you map this model to TCP? Well, the idea was to take as the time slot the round-trip time and to approximate multiplicative decrease by saying, so multiplicative decrease is simpler, like we said. You divide, when you detect a loss, you divide the congestion window by a factor of 2. Additive increase is more tricky to emulate. Ideally, you should start a timer and see whether within a given time slot you have positive feedback. But what does it mean, positive feedback? You may receive 1 acknowledgement. If you have sent 10 packets, you may receive an acknowledgement for those 10 packets. What if you receive it for 8, etc.? So there is a gray zone in between. This is solved by applying this algorithm. This algorithm says the congestion window size, the CWND local variable, is incremented by 1 over itself for every packet that is received, assuming the packets are all of constant size. If they're not, the true formula is something like this. We count in byte, so the congestion window measured in byte is equal to itself plus an increment given by this formula. This formula is hard to understand. If you assume all the packets are constant size equal to MSS, this is what the formula means. So this is a naive formula that is more or less saying, I would like to increase by 1 every time I have transmitted a full congestion window. Right? It's naive because if you do this, that means you should not apply this formula, but you should do congestion window plus 1 over congestion window index 0, the last value of the congestion window before the increase. If your congestion window is 10, and the idea is I will move to 11 when I have received 10 acknowledgements. Because when I've received 10 acknowledgements, that means my full congestion window has been acknowledged. This is my time step. Therefore, I will wait until I've received the full window, which means receiving 10, and then I do 10 plus 1 becomes 11. Here you will do something a bit different. You will do 10. Then when you receive one acknowledgement, you will do 10 plus 1 over 10. The second acknowledgement, you will do 10 plus 1 over 11, not 10 plus 1 over 10. So you will increase a bit less fast than one window, but plus 1 per full window transmitted. But it has implementation benefits. You don't need to store an additional variable. This is illustrated here. I have a source that sends packet. In green, I have the acknowledgements. When I receive, I start with congestion window of 1. Here, the congestion window moves to 2. When I receive 2 packets, it moves to 3. And here, 4. Well, this is the ideal behavior we would like to have, but this thing will approximate something which will be a bit less than 3 or 4. So this is how TCP simulates or approximates the additive increase. So the additive increase is not something synchronous like in the previous model, but it's a constant stream. Whenever you receive acknowledgement, you increment the window size almost linearly, in fact a bit less than linearly. Multiplicative increase is used in Slowstar, uses a similar trick. Here you increment by 1 for every acknowledgement received. So if you send 1 packet, you receive an acknowledgement, you move to 2, then you will receive 2 acknowledgements and you move to 4, etc. You see that at every round you double the size of the window, which is not exactly multiplicative increase because the length of a round, the time it takes for a round, is also increasing. So here too it is a little bit, it's an approximation that's a little bit less, but still is exponential increasing. So the formula in packet is this one. So if we combine those things together, we see that TCP controls the window using the following thing. Whenever you are happy and yet there's no loss, you receive a stream of acknowledgements. Acknowledgements that are true acknowledgements. That means that advance the acknowledgement number. Then you do this additive increase, which has a name in TCP papers and in the code. If you look at it, it's called the congestion avoidance phase. The naming is a bit misleading, like often in comments in code. So congestion avoidance doesn't mean you're avoiding congestion. I mean, the global thing is congestion avoidance. The congestion avoidance phase, I would rather call it the additive increase phase. So you increase the window as long as you receive acknowledgements. When there is a loss, you decrease the window approximately by half, but you do a little detour by Slowstar, which is shown here. So the multiplicative decrease is an abrupt event that occurs when there is a loss, as opposed to the additive increase that occurs like a stream of events here. Let me conclude with this last quiz. We have not finished describing TCP. We will see that there are other bells and whistles for congestion control, but for today we will finish on this. Assume a TCP flow uses Wi-Fi, and by bad luck, like happens sometimes in Wi-Fi, the loss ratio is high. Assume some packets are lost in spite of Wi-Fi retransmissions. We've seen that the design of the internet says we should repair losses locally. In principle, we repair losses end-to-end, except if you have lossy links that have non-negligible error rate. So Wi-Fi has it, but it can happen that the things are so bad that you cannot retransmit. What will happen when a packet is lost on the Wi-Fi link? Lost, I mean lost and not recovered by retransmission. I propose 3 possible solutions. I close the poll in 5 seconds. And the majority is right. Unfortunately, TCP will think it's